Dalton's atomic theory. Although the origin of the idea that matter is composed of small indivisible particles called atomio, meaning indivisible, dates back to the time of Democritus, a Greek philosopher, 460 to 370 BC, it again started emerging as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following. Matter consists of indivisible atoms. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. Compounds are formed when atoms of different elements combine in a fixed ratio. Chemical reactions involve reorganization of atoms. These are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination. However, it could not explain the laws of gaseous volumes. It could not provide the reason for combining of atoms, which was answered later by other scientists. Atom and molecular masses. After having some idea about the terms atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular masses. Atomic mass. The atomic mass or the mass of an atom is actually very small because atoms are extremely small. Today we have sophisticated techniques, example mass spectrometry, for determining the atomic masses fairly accurately. But in the 19th century, scientists could determine the mass of one atom relative to another by experimental means, as has been mentioned earlier. Hydrogen, being the lightest atom, was arbitrarily assigned a mass of 1 without any units, and other elements were assigned masses relative to it. However, the present system of atomic masses is based on carbon-12 as the standard and has been agreed upon in 1961. Here, carbon-12 is one of the isotopes of carbon and can be represented as C12. In this system, C12 is assigned a mass of exactly 12 atomic mass unit AMU, and masses of all other atoms are given relative to this standard. One atomic mass unit is defined as a mass exactly equal to 1/12 of the mass of one carbon-12 atom. And 1 AMU is equal to 1.66056 into 10 to the power minus 24 grams. Mass of an atom of hydrogen, which is equal to 1.6736 into 10 to the power minus 24 grams. Thus, in terms of AMU, the mass of hydrogen atom is equal to 1.6736 into 10 to the power minus 24 divided by 1.66056 into 10 to the power minus 24, which is equal to 1.0078 AMU. Similarly, the mass of oxygen 16 or O16 atom would be 15.995 A. At present, AMU has been replaced by U, which is known as unified mass. When we use atomic masses of elements in calculations, we actually use average atomic masses of elements, which are explained below. Average atomic mass. Many naturally occurring elements exist as more than one isotope. When we take into account the existence of these isotopes and their relative abundance percent occurrence, the average atomic mass of that element can be computed. For example, carbon has the following 3 isotopes with relative abundances, and masses are shown against each of them. C12 98.892, atomic mass 12. C13 1.108, atomic mass 13.00335. C14 2 into 10 to the power minus 10, atomic mass 14.00317. From the above data, the average atomic mass of carbon will come out to be, which is equal to 12.011 U. Similarly, average atomic masses for other elements can be calculated. In the periodic table of elements, the atomic masses mentioned for different elements actually represent their average atomic masses. Molecular mass. Molecular mass is the sum of atomic masses of the elements present in a molecule. It is obtained by multiplying the atomic mass of each element by the number of its atoms and adding them together. For example, molecular mass of methane, which contains 1 carbon atom and 4 hydrogen atoms, can be obtained as below. Molecular mass of methane CH4 is equal to 12.011 U plus 4 into 1.008 U, which is equal to 16.043 U. Similarly, mass of water H2O is equal to 18.02 U. Formula mass. Some substances such as sodium chloride NaCl do not contain discrete molecules as their constituent units. In such compounds, positive sodium ion and negative chloride ion entities are arranged in a three-dimensional structure as shown. It may be noted that in sodium chloride, 1 Na plus ion is surrounded by 6 Cl minus ions and vice versa. The formula such as NaCl is used to calculate the formula mass instead of molecular mass, as in the solid state sodium chloride does not exist as a single entity. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine, which is equal to 23.0 U plus 35.5 U, which is equal to 58.5 U. Mole concept and molar masses. Atoms and molecules are extremely small in size, and their numbers in even a small amount of any substance is really large. To handle such large numbers, a unit of convenient magnitude is required. Just as we denote 1 dozen for 12 items, score for 20 items, gross for 144 items, we use the idea of mole to count entities at the microscopic level, that is atoms, molecules, particles, electrons, ions, etc. In SI system, mole, symbol MOL, was introduced as 7th base quantity for the amount of a substance. The mole is the SI unit of amount of substance. 1 mole contains exactly 6.022140076 into 10 to the power 23 elementary entities. This number is fixed numerical value of the Avogadro constant Na when expressed in the unit mole to the power -1 and is called the Avogadro's number. The amount of substance, symbol N, of a system is a measure of the number of specified elementary entities. An elementary entity may be an atom, a molecule, an ion, an electron, any other particle or specified group of particles. It may be emphasized that the mole of a substance always contains the same number of entities, no matter what the substance may be. In order to determine this number precisely, the mass of a carbon-12 atom was determined by a mass spectrometer and found to be equal to 1.992648 into 10 to the power -23 grams. Knowing that 1 mole of carbon weighs 12 grams, the number of carbon atoms in it is equal to 12 gram per mole C12 divided by 1.992648 into 10 to the power -12 gram per mole C12 atom, which is equal to 6.0221367 into 10 to the power 23 atoms per mole. This number of entities in 1 mole is so important that it is given a separate name and symbol. It is known as Avogadro constant or Avogadro number, denoted by Na, in honor of Amedeo Avogadro. To appreciate the largeness of this number, let us write it with all zeros without using any powers of 10. 60221367 23 zeros. Hence, so many entities, atoms, molecules, or any other particle constitute 1 mole of a particular substance. We can therefore say that 1 mole of hydrogen atoms is equal to 6.022 into 10 to the power 23 atoms. 1 mole of water molecules is equal to 6.022 into 10 to the power 23 water molecules. 1 mole of sodium chloride is equal to 6.022 into 10 to the power 23 formula units of sodium chloride. Having defined the mole, it is easier to know the mass of 1 mole of a substance or the constituent entities. The mass of 1 mole of a substance in grams is called its molar mass. The molar mass in grams is numerically equal to atomic or molecular or formula mass in U. Molar mass of water is equal to 18.02 gram per mole. Molar mass of sodium chloride is equal to 58.5 gram per mole. Percentage composition. So far, we were dealing with the number of entities present in a given sample, but many a time, information regarding the percentage of a particular element present in a compound is required. Suppose an unknown or new compound is given to you. The first question you would ask is, what is its formula? Or what are its constituents and in what ratio are they present in the given compound? For known compounds also, such information provides a check whether the given sample contains the same percentage of elements as present in a pure sample. In other words, one can check the purity of a given sample by analyzing this data. Let us understand it by taking the example of water, H2O. Since water contains hydrogen and oxygen, the percentage composition of both these elements can be calculated as follows. Mass percent of an element is equal to mass of that element in the compound into 100 whole divided by molar mass of the compound. Molar mass of water is equal to 18.02 grams. Mass percent of hydrogen is equal to 2 into 1.008 divided by 18.02 into 100, which is equal to 11.18. Mass percentage of oxygen is equal to 16.00 divided by 18.02 into 100, which is equal to 88.79. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular formula of ethanol is C2H5OH. Molar mass of ethanol is 46.068 grams. Mass percentage of carbon is equal to 24.02 grams divided by 46.068 grams into 100, which is equal to 52.14%. Mass percent of hydrogen is equal to 6.048 divided by 46.068 into 100, which is equal to 13.13%. Mass percentage of oxygen is equal to 16.00 divided by 46.068 into 100, which is equal to 34.73%. After understanding the calculation of percent of mass, let us now see what information can be obtained from the percent composition data. Empirical formula for molecular formula. An empirical formula represents the simplest whole number ratio of various atoms present in a compound, whereas the molecular formula shows the exact number of different types of atoms present in a molecule of the compound. If the mass percent of various elements present in a compound is known, its empirical formula can be determined. Molecular formula can further be obtained if the molecular mass is known. The following examples illustrate this sequence. Stoichiometry and stoichiometric calculations. The word stoichiometry is derived from two Greek words, stoichion meaning element and metron meaning measure. Stoichiometry thus deals with the calculation of masses, sometimes volumes also, of the reactants and the products involved in a chemical reaction. Before understanding how to calculate the amounts of reactants required or products produced in a chemical reaction, let us study what information is available from the balanced chemical equation of a given reaction. Let us consider the combustion of methane. A balanced equation for this reaction is given below. CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O gas. Here, methane and dioxygen are called reactants and carbon dioxide and water are called products. Note that all the reactants and the products are gases in the above reaction and this has been indicated by letter G in the brackets next to its formula. Similarly, in case of solids and liquids, S and L are written respectively. Coefficients 2 for O2 and H2O are called stoichiometric coefficients. Similarly, the coefficient for CH4 and CO2 is 1 in each case. They represent the number of molecules and moles as well, taking part in the reaction or formed in the reaction. Thus, according to the above chemical reaction, 1 mole of CH4 gas 1 mole of CH4 gas reacts with 2 moles of O2 gas to give 1 mole of CO2 gas and 2 moles of H2O gas. 1 molecule of CH4 gas reacts with 2 molecules of O2 gas to give 1 molecule of CO2 gas and 2 molecules of H2O gas. 22.7 liter of CH4 gas reacts with 45.4 liter of O2 gas to give 22.7 liter of CO2 gas and 45.4 liter of H2O gas. 16 grams of CH4 gas reacts with 2 into 32 grams of O2 gas to give 44 grams of CO2 gas and 2 into 18 grams of H2O gas. From these relationships, the given data can be interconverted as follows: mass to moles to number of molecules, and vice versa. Mass by volume is equal to density. Limiting reagent. Many a time reactions are carried out with the amounts of reactants that are different than the amounts as required by a balanced chemical reaction. In such situations, one reactant is in more amount than the amount required by the balanced chemical equation. The reactant which is present in the least amount gets consumed after some time, and after that further reaction does not take place, whatever be the amount of the other reactant. Hence, the reactant which gets consumed first limits the amount of product formed and is therefore called the limiting reagent. In performing stoichiometric calculations, this aspect is also to be kept in mind. Reactions in solutions. A majority of the reactions in the laboratories are carried out in solutions. Therefore, it is important to understand as how the amount of substance is expressed when it is present in the solution. The concentration of a solution or the amount of substance present in its given volume can be expressed in any of the following ways: mass percent or weight percent, W by W percent, mole fraction, molarity, molality. Let us now study each one of them in detail. Mass percent. It is obtained by using the following relation: mass percent is equal to mass of solute by mass of solution into 100. Mole fraction. It is the ratio of number of moles of a particular component to the total number of moles of the solution. If a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as: mole fraction of A is equal to number of moles of A divided by total number of moles of solution, which is equal to Na by Na plus Nb. Mole fraction of B is equal to Nb by Na plus Nb. Molarity. It is the most widely used unit and is denoted by capital M. It is defined as the number of moles of solute in 1 liter of the solution. Thus, molarity is equal to number of moles of solute divided by volume of solution in liters. Suppose we have 1 molarity solution of a substance, say NaOH, and we want to prepare a 0.2 molar solution from it. 1 molar NaOH means 1 mole of NaOH is present in 1 liter of the solution. For 0.2 molar solution, we require 0.2 moles of NaOH dissolved in 1 liter solution. Hence, For making 0.2 molar solution from 1 molar solution, we have to take that volume of 1 molar NaOH solution, which contains 0.2 moles of NaOH, and dilute the solution with water to 1 liter. Now, how much volume of concentrated 1 molar NaOH solution be taken, which contains 0.2 moles of NaOH, can be calculated as follows. If 1 mole is present in 1 liter or 1000 ml solution, then 0.2 moles is present in 1000 ml divided by 1 mole into 0.2 mole solution, which is equal to 200 ml solution. Thus, 200 ml of 1 molar NaOH are taken and enough water is added to dilute it to make 1 liter. In fact, for such calculations, a general formula M1 into V1 is equal to M2 into V2, where M and V are molarity and volume respectively can be used. In this case, M1 is equal to 0.2 m, V1 is equal to 1000 ml, and M2 is equal to 1.0 m, V2 is to be calculated. Substituting the values in the formula, 0.2 into 1000 is equal to 1.0 into V2, V2 is equal to 200 ml. Note that the number of moles of a solute NaOH was 0.2 in 200 ml and it has remained the same. That is 0.2 even after dilution in 1000 ml, as we have changed just the amount of solvent, that is water, and have not done anything with respect to NaOH, but keep in mind the concentration. Molality. It is defined as the number of moles of solute present in 1 kg of solvent. It is denoted by small m. Thus, molality small m is equal to number of moles of solute divided by mass of solvent in kg. Summary. Chemistry as we understand it today is not a very old discipline. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in 3 states: solid, liquid or gas. The constituent particles are held in different ways in these states of matter and they exhibit their characteristic properties. Matter can also be classified into elements, compounds or mixtures. An element contains particles of only one type, which may be atoms or molecules. Compounds are formed where atoms of 2 or more elements combine in a fixed ratio to each other. Mixtures occur widely and many of the substances present around us are mixtures. When the properties of a substance are studied, measurement is inherent. The quantification of properties require a system of measurement and units in which quantities are to be expressed. Many systems of measurement exist, of which the English and the metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units, International System of Units. Since measurements involve recording of data which are always associated with a certain amount of uncertainty, the proper handling of data obtained by measuring the quantities is very important. The measurement of quantities in chemistry are spread over a wide range of 10 to the power minus 31 to 10 to the power plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the number of significant figures in which the observations are reported. Dimensional analysis helps to express the measured quantities in different systems of units. Hence, it is possible to interconvert the results from one system of units to another. Combination of different atoms is governed by basic laws of chemical combination. These being the law of conservation of mass, law of definite proportion, law of multiple proportions, Gay-Lussac's law of gaseous volumes and Avogadro's law. All these laws lead to Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to C12 isotope of carbon, which has exactly value of 12U. Usually, the atomic mass used for an element is the average atomic mass, obtained by taking into account the natural abundance of every isotope of that element. The molecular mass of a molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. Molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular masses. The numbers of atoms, molecules, or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 to the power 23. This is known as 1 mole of the respective particles or entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The amount of substance present in a given volume of a solution is expressed in the number of ways. Example: mass, percent, mole fraction, molarity, molality, etc.